Okay, here we go. 2690. We're going live stream today. It is Monday, November 1, and I am already losing my voice. Excuse me. And what we are doing, I got my master schedule here. Actually, let me drop the link real quick for everybody. Hold on a second. Okay. Alrighty. I got a question on Discord. A student asked when projects would be open for submission again. We need to open the projects up again. All right. All right. So yeah, projects should be open back up. I'm granting some deadline amnesty, just given all the confusion with everything. Okay, so we ended at the end of this lecture, which is dictionary based compression. Man, I'm really sorry. I don't know what's going on with my voice. And today basically is just JPEG. We're doing the end of 20 and then 21, second half of 20, well, the end, and then 21, which is all about how JPEG works. Then we're going to be doing MPEG, and I'm going to do that one as well in advance of class. So, Kimberly, yeah, thank you. Hang on a second. All right, Kimberly said she's got that taken care of. Thank you very, very much. Okay, thanks. Awesome. Thanks, Kimberly. And in fact, Kimberly, if you want to hang on when we're done, it would be good to jump on a voice chat if you've got a minute right afterwards. And you can like I said, you can jump on YouTube. We've got video as well going. Okay, so let's talk about JPEG. Quick overview. And I'm just double checking again any comments. And again, if you're live in class or whatever, and you want me to join, and you want to listen in real time on the voice channel, that's just great. And I can jump over there as well on Discord and share screen. It does save a little bit of the liveness. There's usually about a 5-second delay or so streaming to YouTube. Okay, everybody uses JPEG, right? Everybody knows what it is. But there's a couple things to know that I think are kind of critical. And then we're going to walk through sort of how it works, but we're gonna do a little bit of hand waving. There's a bunch of cringy, crappy math going on JPEG. I think it's pretty ingenious, and the art, basically the intellectual property, original invention stuff goes back to like 1972. So it's some pretty gnarly matrix math and other kinds of stuff that's beyond our scope. But and then again, as you probably know, I've got my big screen this way, so a lot of times when I'm looking at what you see on the screen, I'm looking this way. So just heads up on that. But number one, specifically built for color photos, okay, and photos of art. It is less suitable for grayscale, it's really not suitable for, remember when we were talking about fax transmission, we were dealing with black and white pixels, right? Just a set of black and white pixels. Really not suitable for that. Cartoons, things that have like, it's better for smooth type graphics, basically, than it is for graphics with sharp lines. Um, so that's kind of the first two bullets. The fundamental principle is that it's so we sort of said they I wasn't there, but you know the idea was to say um, we need to lose information. In other words, we're going to do something lossy. If we try to hang on to all the information with a complete bitmap of every pixel, it's just going to be way too big. It's just going to become crazy. And for a lot of purposes, we don't need that much resolution. Things down at the bottom, next bullet, things like medical imaging, astronomy, photo enlargements. You know, you want to print a really big poster, you know, and you want to do that digitally, you have to have all the resolution to print that thing, right? You want to do a wall-sized poster and you're going to print that thing digitally, you need really great resolution. Spy satellite, you know, whatever. Anything you really, really need the precision, you can't, you know, you're not going to use a lossy compression algorithm. You can't do it. Well, one of the ways to do lossy compression is to say, well, what's the domain? Like for example, in it's not on this one, but it's on I think one of the other slides maybe. But you can compress, for example, audio by knocking off the high frequencies. You get a lot of resolution in the high frequencies on audio, and you can cut that off and be okay having a conversation. You just don't want to listen to a symphony orchestra through that, but you can have a conversation. So an understanding of the use case of the use model has is a big factor in terms of like I know what we're expecting. I know it's voice, or I know it's certain kinds of graphic images, and then based upon that, what I know is coming. I can decide what I'm going to let go of and what I'm not. Right. So with fax data, because we knew the nature of the fax data, we could do like run length encoding with how many black and white pixels. Well, for if we said let's do something with color images that have a lot of blend in the colors, like you see in a painting or something like that. And so it turns out that human vision has a high level of sensitivity to brightness and a lesser sensitivity to changes in color, or hue. So we can more readily tell, and this is just human physiology, it's just genetics, we can tell more readily that something's brighter or dimmer than something else, but we have less of a easy time differentiating this shade of red from that shade of red, and it's sort of okay as long as the brightness is the same. And that was kind of the big insight relative to JPEG. So the idea was to not compromise on the brightness, but compromise on the color. So that was the fundamental idea. And then what that allows us to do, because we're going to compromise on the color, we can compromise, and the thing was set up so that we can compromise a lot and save a lot of space, or compromise very little and burn a bunch of space. Okay. I just need to check something real quick on Discord messages. Um, Hang on. All right. um, okay. Yeah. So basically, you can do a trade-off between size and quality. That's the bottom line. That's kind of the core. I can get higher quality and burn more space to get it. I can do lower quality and save space while doing it. That's it. That's the fundamental idea. Okay, now the way this thing works is well, actually before we get to that, and I changed the if you have access to the slides online, change the order here just a little bit. This is the representation of a pixel in any kind of random graphic image. There's an X and a Y position, and then there's a Z axis, which is the color, right? So at this location, X and Y, there's a particular color, Z, and that is at the resolution of individual pixels, okay? And there can be a lot of pixels, obviously, in a given image. The way we deal with this, we take that source image, which is built in that manner with an XY location and a particular numeric representation of the color of the pixel. And what we do in the process of JPEG compression is we do this thing called discrete cosine transformation, and we'll talk a little bit about it. And this stuff is really grungy. And then we do a process called quantization. And when we're done, we have an image that we can then encode, and that's our compressed image. We obviously reverse the process on the other side. It turns out, well, this is what we're going to talk about. This DCT is a transformation process whereby we take something that, well, we'll get into it, that essentially changes the form of the data so that we can then do a quantization, which is the phase at which we decide what do you want to let go of to save space. That's what the quantization is all about. The encoding then is to do certain kinds of lossless compression. So I can take my final answer and encode it in a way that I can get that final answer back. I lost information in the quantization phase, okay? That's the bottom line. And this, I got 2 slides of intense ugliness, and then I've got the homework question, which is actually about LZW, so we're not even going to touch it. All this is really trying to say, and I don't think there's anything in the exam stuff that's really in detail about this, other than to say that you can take signals that are in a time domain so that they look like this. There's a frequency across a certain amount of time. So I've got F, I've got 3F. As you can see, there's 1, 2, 3 waveforms. And I can convert those so that I can convert those into a frequency domain that says that this is my frequency and that's the amplitude. It's a different kind of notation. And then I can tack on another frequency like 3F. When I add these together at the bottom, I pick up this kind of a representation of a waveform. The wave itself looks like this one here with F, this one here with 3F. When I add those together, you can see I get a different looking waveform, but I can add them together this way just by having them on this scale, on this frequency scale. And as you can kind of tell, it's going to spread out real quickly. And one of the things that sort of suggests is that as you get further out there, you lose certain kinds of information. In other words, when you add finer and finer frequencies, you make less and less of a difference on the wave itself, okay? So, for example, if you take this waveform right here, where it's starting to, you got it this way, you could call that I'm on, I'm off, you could do that. But when you add all those frequencies together, it starts to resemble a step function, more of a square wave kind of a function, right? So I can add more and more and more of these fine things, but it makes less and less of a difference. So the whole principle of that, and we're going to be, again, done and on to the next slides, but the main point there is that I can lose higher frequency information. And as I do that, I don't lose, if I'm losing information in color and it's higher frequency, higher resolution, Essentially, those go together. I'm not losing anything, or not much anyway, from a perception perspective. Okay, and so let me jump over to. This is really a continuous lecture, which is about DCT and quantization. All right. So remember again, we had that step of DCT, quantization, and then encoding, and that was JPEG compression. What this is meant to illustrate is that a classic image encoding scheme is RGB, and these are the original images on the top here. In RGB, there's a red version, a green version, and a blue version of the thing. When you overlay those three versions, you get the top one. Okay, and so there's a separation, and you encode them with a red color, a green color, and a blue color. Okay, and with some value, right? And when we do the kind of graphics you've probably played around with, you're used to seeing some resolution of red, green, and blue. Well, it turns out that there's a different one called YUV, and it has some other names. But the idea with YUV is that it separates out the luminance or the brightness as a separate image, and then what they call U chrominance and V chrominance. So it's it's a blue luminance difference and a red luminance difference. The main thing to just understand is that you've got essentially two ways of encapsulating and encoding or encapsulating the color, and then an overlay of brightness. Remember that human vision is more readily able to differentiate brightness than it is to differentiate color. And so this allows us basically to preserve the brightness and then to compromise on the color. So we can like lose information on the color. And as long as we preserve information on the brightness, we're going to do a pretty good job of approximating. So here's what happens. We take the RGB image that we're trying to encode as a JPEG, and we grab, so in this case, we're looking at a 16 by 16 as our case in point. We're going to look at this color frame as a 16 by 16 pixel region. We take, let me see, we take that entire 16 by 16, we carve it up, okay? And what you can kind of see here going on, and I need my glasses for this because it all starts to get kind of tiny, and I hope you can see my mouse. This basically, these 4 pixels, you can see they're just different colors here. We take a brightness representation and capture it, okay? We then take, and it talks about how we kind of split this up into 4 8x8s. We then take this 2 by 2, and we take the average of this color in the U component and the average of that color in the V component. And this is the part where it starts to get sort of grungy and ugly. But the bottom line is we grab the color and we grab the Y representation of the luminance, the brightness, and we manage these guys separately. And then this is the part where I'm going to do a lot of hand waving, okay? Because this is going to be the bitmap image file containing these Y components, the brightness, pixels between 0 and 255. And then that's an input matrix. And then we're going to create, and this is the part again where honestly I've been through it. I've really never known this until it was lecture time for this. I've never been through this at that level of detail. And I think I'm probably still a little bit inadequate right now. But the bottom line is, and a lot of this doesn't really matter, honestly, for our purposes, other than to say that there's a DC coefficient in green and the rest of these are AC coefficients. The DC coefficient is basically the color sort of intensity if you did the entire block as a single color. It also allows you to create a mapping on this guy right here. Notice that this guy has, 8 across and 8 down. There's 64 different patterns that they call DCT basis functions. This mapping essentially creates a mapping onto this basis function. Now, the part that it's going to be difficult to see, and so I'm going to actually do something that I hope is going to make this a little bit more reasonable. But I'm going to try to take this little kitty, and if I can blow this up big enough, now I'm all maxed out down here. Yeah, I don't know if I can make this big enough for you. Come on. What we have here is a cat. There, we're getting a little bigger. Okay, there we go. Scary kidda. All right, but what I want you to notice is the patterns. The cat's actually built out of these. Okay? The cat is built out of these patterns. Notice these guys, and notice that they're kind of symmetric across the diagonal. Okay, so if I jump back here to the cat again, do you see it? Like right here, right in here, you can see horizontal lines, and that's kind of approximating the whiskers. And yeah, and then you can see what you can basically see is that as you apply, we'll get back to it, but as you apply a higher resolution, you have finer representation of the shapes in question. And then as you get more and more, as you lose information, you're essentially over here with more, suddenly you look like you're Minecraft. But even out there, you can see patterns, and those patterns are maps, okay? They're maps back to, let me get this guy, back. Sorry, I'm trying to get this guy back over there so I can kind of broadcast it. Throwing him on my other screen. Okay. And the truth is, like I said, I've been through this, and it's a lot of voodoo magic, a lot of math, a lot of matrix stuff. But here's kind of the bottom line, the things to just sort of understand about this. This DC coefficient, when you're looking at the kidda, and you see all the way over here to the left where it starts to be full block, that's the application of the DC coefficient, the most coarse-grained version. and then you get higher frequencies as you move out along the AC, which are called the alternate coordinate, if I'm not mistaken, coefficients. Would have been handy to have those in the slides. And the whole point just being that these coefficients right here give us a mapping into this. So you see there's the DC coefficient. So when that's your value, you get a straight up block of a single color. Otherwise, you get one of these patterns, okay, based upon the value you get here. Now, the other thing that's going on here that we got to get to is the quantization, which is where some of that decision making happens. So here's the idea. These bullets kind of are trying to express the idea. When you move away from the DC coefficient and you move down the diagonal, down and right, you get higher frequency elements with generally smaller values. And those elements are less critical for, telling what the issue, what the image is. Again, right here, what you're doing is you're moving down and right. So as you notice, when you go all the way down the diagonal, you get to a kind of uniform blend here and, different shapes over here. But the further down you get, you can tell the image with just that, or even with just that. But if you get down here, you have a lot more information, all right? But we can discern without it. And so what we basically do, and again, I'm just going to keep apologizing, you convert from that waveform to a frequency domain, then the DCT recognizes the data that can be discarded. Now, how does it do that? It does that during the quantization. But basically what this is doing is taking the information, well, it's actually in the previous slide. I wish it was together here in the same slide set. But that part where we're adding information and that wave is looking more and more like a square wave, right? This essentially is taking all the various frequency information and sort of separating it, differentiating it, so that we can say, well, let's just lose some of the information. If we lose some of the information, we'll still probably be just fine. And so what we do, right, it essentially allows us to identify the frequency information we can discard. We can't do that with the original pixel matrix. So there's the original pixel matrix with all the values. We can't do it with that because we can't tell which ones are more important to the overall quality. By converting it through magic into a frequency representation and frequency coefficients, we can tell which ones are more or less important. And they're less important as you move down and right. That's the bottom line. So the most important data, the less important data. Higher frequency, higher refined, lower frequency. Okay. Oh, and then here's the part I was talking about where the phone, filters our voices into a more reasonable channel, right? But you've lost information. And there's the cat. So this kind of just shows you, it's kind of a nice picture from the Wikipedia JPEG entry of high resolution. And then as you get bigger here, and I can't zoom in right now with this, but as you start to zoom in, you see the pixelization, the pixelation, and it's pretty obvious, right? But what you're basically doing is you're starting the full image is is all the way down using all this information. And as you move left, as I move left on this picture, I'm moving up and left on the DCT coefficients. So as I move this way, I'm losing information, and then you're getting more and more pixelated. I hope that makes sense. It makes a level of sense to me, and I've not been through the deep math. Having done this DCT, I can now perform this quantization. So here's how we do the quantization. We take that DCT output matrix, right, which we talked about before, and what we basically do is we take now, what is this quantization table? The quantization table essentially, you know how when you go to save a value, you save an image as a JPEG, and it'll give you usually a slider. So it'll be like really high res, but a lot of data, a lot of, it's going to take more memory, or you can have it be, rougher image that takes less image. It's an image quality slider, and the higher the quality, the more data. Well, that's kind of what's going on here. But as you move that slider, you're actually selecting different quantization tables, right? Now notice, and then all you do is take the element of the DCT table, divide it by the same element in the quantization table. Notice, and then you're going to get a quantized output matrix. But notice that as you get big values here, and you have to round it, As you get big values here, and you round it to a whole number, okay? Well, to an integer. As you get large values down here, and then you take these small numbers and divide them by these big numbers, it rounds to 0. See what happened? You just lost. So all of those are the equivalent. And when you take that to its extreme, everybody becomes 0 except for the DCT, or what do we call that? The DC coefficient. And there's the DC coefficient. That's when you get to this situation, which is when you get all of this big mass of gray, because the DC is the only thing that survives and the rest of the data is lost because we chose a certain quantization table. Hope this makes sense. The only thing that I can see so far, and maybe Kimberly can jump in, that's sort of like on the homework so far that I can see, is this process of doing the division, okay, which is right. We'll come back to that goofy picture, but it's right there. What's the quantized value? What's the value after being decompressed? So you can kind of see what the level of compression is. And this gives you an example of how to do it. But I hope that intuitively you can kind of see that if I gave you a quantization table that was all 1, then all of this would be preserved. But if I gave you a quantization table that gets bigger as you go down at the bottom, then I'm going to basically say I care less about what's down at the bottom to the right. It's a little grungy. It's, in my view, having taken over week number 2, in my view, this is the ugliest crap we've dealt with so far in the class. And I think, fortunately, we're not, needing to go all the way down to that low-level grunge to do this thing. But so here's the idea. The quantization reduces the number of bits needed to represent the output matrix. So by selectively reducing the precision of the value stored in that matrix, thus introducing loss. If we just said, yeah, take this whole thing, we'd have a better image. But instead, we take this quantization table, which turns a bunch of these into zeros. And when we turn all those into zeros, we're losing information. Okay, but we're also saving space. So this is an example, and the reality is that via the transmission, I'm not sure you can tell, but that's 6-to-1, so it's minimal quantization or loss. 14-to-1, 37-to-1, and then now you're going about 100-to-1. You can see, you should be able to see the pixelization. Let's see, Dallin, are the quantization tables pre-generated, known, or how are those values generated to know what you're dividing by? So, Dallin, my understanding is that they're pre-generated and you just use one. you use the one that represents the kind of loss or savings. That's my understanding. Um, yeah, and so what's happening, is what's really fascinating to me is that the figure on the left, the image on the left, is still 6-1. Now the problem is that you're in a masking situation because we're transmitting all of this via YouTube, which is already doing compression and losing resolution. But even with that, I suspect, can't you, for those that are commenting on Discord now, it's got to be the case that what you see on the lower right is a worse image, even via YouTube. I'm going to imagine. Zach, can I get a confirm or deny on that? But it really has to do with which table you used. Back to Dallin's question. And then the rest of it's actually easy, having gone through all that, because the rest of it is just the encoding. Yeah, so you can see it, right, Seth? How that's looking. The remainder is just encoding. Now, by the way, so who said that? Seth said top two look pretty similar. What's interesting is I'm looking at it on my screen, with my glasses, and the reality is that the top two look pretty similar to me as well. I can look at specific areas and I can see that there is greater clarity on the left, but it doesn't look pixelated on the right where I'm at. Well, there are a couple of spots where there are artifacts. So that's interesting. Okay, let me talk about encoding and then we're going to be done with this for today. The encoding is the easy part. So I started with this DCT, this whole elaborate encoding thing. And when I show you, if I showed you all the grungy math, I mean, I didn't go like carefully through it myself. It would have taken me hours and hours and hours. But it's pretty ugly looking. And then there's this quantization, which is actually a pretty easy step. Once I have backing up, once I have this DCT output matrix, which is what we were building right here through magic, once we build this table, which has higher frequencies, down the lower right, as you can see there on the axes left and right, or kind of X and Y, right? And then I'm quantizing. The quantizing is actually a pretty easy step. And then again, from this, I've encoded now the representation, the data representation. Now, and again, how exactly I encode that, I don't even know. And I haven't looked it up at that level. But once we've got that value, now encoding it becomes really easy. Here's what we do. We take all the DC coefficients and we apply differential encoding. Remember, differential encoding says I'm starting with one value, or maybe I start with 0 and then I give me the first value. Then I want the difference between that value and the next value, the difference between that value and the next value. You see how that's going to be more beneficial when images are smooth and the similarity between things is going to be close. So I take all the DC coefficients and I do that differential encoding. I take all the AC coefficients and you can kind of see right here, that's the DC coefficient. So I take the remainder of those, 18, -9, -3, -8, 1, and I do a run length limited encoding. And what you ought to be able to see is when the run length encoding is going to really shine is when you hit all the zeros, right? As you lose resolution. I mean, you may luck out as you can see here. If we go, where are we at here? Yeah, yeah. -3, 1, -2, 4, -2, 4, 0, 3. 0, 1, 1. There's a little, run length encoding. 0, pair of negative ones. Now, boom, 3 zeros in a row, a negative one. 1, 2, 3. Well, everything else is a 0. So I just saved half of all of that. And that's where the big savings comes in. So I use run length limited. Sorry, I keep saying run length limited. Run length encoding. And then when I'm done with all of that, and I've just got this massive numbers, then I do Huffman encoding or some other kind of entropy-based encoding, so that I just do like kind of like a dictionary, you know, find patterns, store the patterns. So it's literally three layers of encoding. Well, the DC coefficients are encoded one way, the AC coefficients are encoded another way, and then the whole thing gets a kind of like a Huffman. That's it. See, it goes a lot faster when we're not in class with you guys asking all your great questions. Let me hit a couple of other things. So that's it for the lecture things. And again, on the one hand, I apologize that I don't have a finer level of, resolution on my understanding of the gory grunge. Not that I would want to throw it at you at that same level, but the reality is, if I had a deeper understanding, I think I could simplify Dave's slides better, and make them make more sense from an intuitive perspective. But at least I think it gives you an appreciation for what's going on when you do, that kind of JPEG encoding. Um, let me hit a couple of sort of exam question kinds of stuff, because I'm going to later on. I'm going to later on, maybe tonight. The remaining one we have between now and, I mean, you've got all the material for the exam, but the material that we're supposed to cover on the schedule prior to next week. So there's not going to be any class next week on the 8th or the 10th, no class. And Dallin, yes, yeah, Dallin, that is, I'm pretty confident. What do you do on the other side to undo the quantization? Yeah, you would just multiply your way back, because you got to get to that. You got to get back to that digital matrix, the DCT, to represent it. But you have to apply the same quantization table, of course, right, to get that value back. And this is why it's lossy. Where there's a 0, you can't get it back. Those just become zeros. So, interesting. Anyway, yeah, so I'm going to do, again, in order to just sort of save time for me, for everybody, we did reach a point, for those of you watching this that haven't been regularly there, we did reach a point where we had 6 or 7 people physically in class, and they were the 6 or 7 people who had class in the building the hour or two just before. So that sort of made it a much easier decision to try to just do this, because it's quite a time sink to show up when, and then I post it on YouTube anyway. So as long as I'm posting it on YouTube, this allows me to stream it to YouTube so it can be live. And then, just try to hit me up on Discord. But what I'm going to do is for MPEG, which is the remaining lecture for this, we were going to try to, if you remember, we were going to try to take the 3 lectures, 20, 21, 22, do them in this week, which we're easily in a position to do. When we come back from the week off for the testing, Seth, I hope you're doing well, man. I hope you're hanging in there. Thought about you. And since we're not in violation of HIPAA, since Seth said it, he got whacked with the Rona, and so we all really hope you're okay. I mean, that can just be so brutal. But anyway, when we get back, it's all security. We've got 6 lectures, got 2 lectures, then Thanksgiving, and then 4 lectures after Thanksgiving. I'm going to do the best I can to try to jump ahead on these, and when I have them prepared, jump on and stream them. Then if you're in an ideal situation where you'd prefer to just like watch it during class time because that's what you're scheduled for, then just watch it during class time. And if you want to get ahead, it's there ahead waiting for you. But it'll save me a ton of time getting to campus and back just to teach the one class. We've been talking a lot about overhead, and the overhead on that is remarkably high, especially since we have the technology and we have folks like Seth and Michael's out of the country and can't get back, and there's just enough people that are already dependent on what I put on YouTube that we might as well shift, and then we'll get out of it. But I'm going to try to climb ahead as quick as I can and get through these 6 lectures after I finish MPEG, which I'm going to try to do it tonight. Alrighty, my friends, that's all I've got for now. We can do maybe we can do a little bit of an online Q&A during I don't know, man, maybe during I don't know, sometime. I'd like to do a little bit of Q&A, in advance of the test. Help sort of separate some of the test questions. I already made some changes to some of the test questions, but all right, I'm gonna stop. I'm gonna shut it down if that's okay with everybody. And let me just make one last sort of double check. Okay. Yeah. Okay. Dallin is typing. I'm good. I'm wrapped. If you guys are okay with being wrapped, unless there's anything else chat wise, comment wise. I'm curious how many people are live on YouTube right now. 5. There you have it. Okay. Okay. I'm shutting. Um, I got Dallin and Seth typing. Yeah, Seth, let's just jump on Discord while you're still recovering. Um, if I do an example of a test question for this set of slides we did today, Dallin, let me see. Well, yeah, let me hit a couple. Some of these, I don't want to repeat ones we did where it's on YouTube in class. Like we did entropy calculations, we did that in class. We did a sample Huffman table in class. So you can hit those online, hit those on the slides. The biggest thing, a couple of just some pointers. Let me just do that, Dallin. Okay, we'll do some pointers. Here's a question. Which compression technique, and I would say techniques, think of it as techniques, encodes the digital value of an analog sample based on the change from the previous sample, right? Now we talked about this with encoding the DC coefficient, right? And we said we use differential encoding. Differential encoding, there was a couple of words, differential and delta. Those are key words. Differential means difference, delta means difference. So it just has to do with the idea that I'm going to give you, if I'm going to say, oh look, here's a waveform, and at a given frequency, I'm going to say you were here, now you were 5 higher, 2 higher, the same, one lower, and it's more like mapping it as it goes instead of it's all relative. But the key word you're looking for is differential. So if you get confused, but you should definitely understand, that differential PCM, which is pulse code modulation, um, using delta encoding. We talked about that in class. It's in the lecture stuff. Um, Here's one. What statement about compression algorithms is true? What do we know about compression algorithms? Sorry, about compression algorithms. And it's a bunch of stuff about lossy and lossless. Let me hit these for those that are here. And again, there's a delay because we're not on Discord on voice. We are on YouTube. But one question might ask, or one answer might give you, um, uh, that they tend to produce similar compression ratios. No, lossy algorithms give you more compression because you lose information itself. It's one thing to find smarter, better ways to compress, but with lossy, you're starting by losing the information itself. Um, how about this one? Lossy algorithms are never appropriate when the data will be presented to a human. Well, no, that's not true, right? Lossy algorithms often are fine when you're talking to humans. In fact, sometimes, lossless algorithms are also sometimes really valuable, like X-rays and things like that. So then the question is, who gives you better compression ratios, lossy or lossless? Lossy is always going to give you better compression, bigger compression. So, when we talk about each of the compression algorithms like Huffman, that's lossless. We don't lose anything. The dictionary-based approach, lossless. Run length encoding, lossless. JPEG, lossy. Every one of the ones we talk about, know whether they're lossy and lossless. But this is the key. Don't just sit here and make a big memorized list. If you know how Huffman coding works, you have to ask yourself, is there ever a step where we literally lose information, where we lose data in the first place? Huffman, no. Dictionary, no. Run length, no. There's never a part where we say, change that number. But with JPEG, is there ever a point where we change the data itself? And the answer is yes. So that's obviously going to be lossy, right? So that's some those are some examples. And the rest of the stuff I think that we hit that are relative to test number 2, we've hit on, again, in class. Let me see. Here's one other one that I think a lot of people missed. I think there was some homework about this one. Which of the following is not generated by a stub compiler? And again, we talked about that at length. And you should just go back and review what gets generated by a stub compiler. Okay? Just remember that a stub compiler generates C code. An executable file is made by compiling C code. It's how you get a .exe file, an executable file. So stub compiler does not get you an executable. Anyway, I hope those should be helpful. At least a few pointers. So, all right, Dallin, thanks for asking for your compatriots. I hope that was helpful. I'm going to shut it down. I will see you later. I'll post. I'll send a message out on Canvas, and I'll post to Discord as well when I've got the next one, Lecture 22, recorded and posted. Later, my friends.